I see Akash on the window. Good afternoon, or good morning for you, actually, since
Good morning,
if I'm not mistaken, you're based in the US. We will be talking about cloud security again, but most, I think, focusing on data analytics. This is a huge topic for space because besides collecting the data with satellites and space assets, taking them down through RF downlinks, storing them in the cloud, then one of the main purposes is to be able to analyze this data to get some value out of it. And this has to be done securely. And I think this is the topic of your speech, Akash.
Yes.
Then, if you are ready to share your slides, you can also do the trick of PowerPoint as a background, as we try to do at CYSAT. I don't know if you can do that. Otherwise, the good old way will also work.
Yeah, this one's not letting me do that for some reason.
Oh. Do we blame the CTO, like you mentioned this morning, Alex?
Yeah, sure. It's all my fault. So,
I've sent it to Constant. I don't know if she can share or to.
Can we share the slides of Akash or not? No, I think it's easier if you share your screen.
Okay, will do. Please let me know when you can see it.
Yep. Do we need some time to figure it out, or?
It's pulling up now.
I see something is loading. Yes, we see your screen. Perfect.
Great. As a virtual background, or?
Yes,
yes,
even with the virtual
works.
background. Congratulations, you have liftoff, Akash.
Nice.
Go ahead, please. Thank you.
Yeah. So today I was going to talk about reliability of AI solutions in space. So, as most of you know, there is a huge amount, petabytes of data collected from space for both commercial, civil, and government purposes. A lot of these images, signals, and a lot of the intelligence gathered from space is used for AI analytics, machine learning, and particularly deep learning. And so what I wanted to show is how, one, you could change and manipulate just a little bit of the data to get completely different results. And two, what the tiers of security are. So from space, there are a lot of attack vectors, as you know. There's a network to think about. So how are you connecting uplink and downlink from satellites and space assets? There's the particular devices themselves. So what are the supply chain issues when you're creating and putting the hardware together? What does the identity look like? So who's all able to access the type of data that's coming up and down? Specific applications. So when we talk about applications, we're talking about edge compute, edge stack intelligence, a lot of work on satellites, so you don't have to bring all of the data down. What does the total infrastructure look like? So, a lot of LEO proliferation in space at the moment, and then what type of data are you augmenting or using sort of your artificial intelligence and machine learning programs on? And so that's a little bit about what I'm going to talk about. We assume that it's hard for most people to infiltrate the top 5, but how can you manipulate data to completely change your results of AI models, and how do you do that from a space perspective? So one thing I'm going to talk about is a civil use case. So NOAA, NASA, a lot of these agencies use artificial intelligence and deep learning to now predict hurricane intensity and track prediction. So, we take photos from a lot of these NOAA satellites. We have a network, if you will, of aircraft, water in oceans, and spacecraft sensors, and they put all of that data together to get sort of these predictions. And there's a load of features, 11 features in total, but we're going to focus on sort of the 3 main ones, which is wind intensity, which tells you how strong the hurricane is, latitude and longitude, which just tells you the positioning. And so we've created a lot of, and Microsoft and through my PhD, a lot of open source and knowledge transfer. And so you can sort of see the tech and software we've used, and there's a link if anyone wants to download any of the research. So this is what the model architecture looks like. So you have inputs, and then you have sort of the guts of the AI model. You see the bidirectional LSTM, which stands for long short-term memory. And so here's what a lot of algorithms like natural language processing use, right? They not only can tell what's happened in the past, but when they're predicting the future, they take the past into account. So say you're reading a book, right, or a sentence. If you want to predict the next word, you might need to know what the sentence or the paragraph before it was talking about. And so LSTMs are a great way to do that. And they're called long short-term memory networks because they can sort of remember the long and forget the short if it's not useful for the model in general. And then you can see we've added what's called a time distributed dense layer, which is what you need for time data, right? So hurricanes, anything to do with space is very time focused. And so it's always a linear path forward. You usually don't go back. And so we've added that layer there. And then, what are the outputs? Wind, latitude, and longitude. And then we show, with just a slight manipulation, how just in this slight manipulation in the data, can you change the prediction totally of a space application? So here's some data and skills. So NASA, NOAA, and a lot of other hurricane predictors use an equation called skill. So how skilled are you? And that's a very ambiguous term almost, but it's how well can you predict, or a model predict, the intensity and track of a hurricane or a storm or anything else compared to what the traditional models are. Now, the traditional models are fairly old, from the 60s and 70s, and they still use them today. So how much better are you than the traditional model at doing these comparisons? And so you can see in the green table here, the normal predict is the first 63, 39, 32, and that's a wind prediction, right? And then the ground truth is data after the fact. So what actually happened was the ground truth. So 60, 40, and 35, as you can see. And then the manipulation predict right in the middle, you can see that it's quite different. So, the difference between 15 for that completely changes how you are in terms of skill in predicting the wind, and in turn how forceful the hurricane is. And you can see it compared to the bottom. So the OFCL and the OFCD are two of the official One is the European and one is the American model for generating hurricane tracking predictions. And on the next slide, we see here what the difference is in latitude and longitude. So the green is for Hurricane Barry, and that's what we did. For the green is 0.000 is the ground truth, right? And then the blue is what we changed from a data input perspective, not an output perspective. That the output was changed slightly just due to the prediction error. And then the red is the actual AI model prediction of where the hurricane was going to be. So you see the red and green are almost on top of each other, and these are predicting the center of the hurricane. So you can see by just changing, 10 1,000ths or 0.01% of a latitude and longitude in the input data, do you get a change in where the output or the prediction is. Now imagine you did this on a larger scale for more than one hurricane. I changed one hurricane input data and we have and the input data lasted from 1873. So we have data from 1873 all the way to 2018, and that was a test data set. So you can imagine the thousands of hurricanes we have, multiply those number of hurricanes by 11 input features, multiplying them by an average of 24 time steps per, and you can see how your AI model can drastically change by a small tweak in the data. And from a cybersecurity perspective, the way that cybersecurity is handled now, it doesn't necessarily, if you're doing AI models and deep learning, machine learning algorithms, it doesn't matter now if I hack into your network. It doesn't matter if I hack into your infrastructure. It doesn't matter if I hack into your devices or if I gain root identity access, because with a small amount of change in the input data, you can completely fool an adversarial AI learning model. And this is a case for hurricanes, right? And while they do have drastic effects of, where do you send help and resources? Think about what an adversary can do if they're changing a model for something else completely. And so from a cybersecurity perspective, we're thinking about how do you protect your data? How do you protect and how do you realize when your data has changed? So a lot of the work that we've been doing is in creating what we call zero trust data sets, and not just a zero trust architecture, but it's zero trust data sets, because a lot of what artificial intelligence and machine learning is doing now is what we call transfer learning. So you're adding data as you're collecting it. So as a weather satellite is flying over, or there's an aircraft sensor or water sensor on the ground, you're adding that data to your input data set. But how do you know when to lock down that data set so that you can't make any changes to it? So an adversary can't make any changes to it, which inevitably changes how your machine learning model behaves in the end. And that's a lot of what the research that I'm working on now from a space perspective deals with. And so I think we have like 5 or 10 minutes for questions and answers. So any Q&A there?
Thank you, Akash. Very interesting research. I think it relies to the broader topic, actually several topics. First, the authenticity of the data that are collected in space. This is something we'll discuss tomorrow for the onboard part, like what you need to do on the satellite itself to make sure that the imagery or any data that are collected are actually authenticated and confidential. And then the other topic to me is the big question mark on how you secure sensitive code, especially AI, ML models, as you demonstrated today, especially in a public cloud setting. We talked a bit about confidential computing this morning, Akash. I don't know if you're familiar with the concept.
Yeah. So Microsoft, we have, and I'm not trying to plug Microsoft, but Microsoft, AWS, most cloud computing companies have some version of, public cloud, private cloud, hybrid cloud, and then we have cloud that are government specific at different specification levels. So, the number of users, the even the networks that those clouds are accessed on are significantly different than what folks use for public internet and public cloud. Hybrid cloud, is one that we're often asked about. So how do you take on-premise architecture, on-premise server racks, and that type of compute and storage, and augment it with public or private cloud and some instantiation. But I think what matters most is to be able to get sort of, once you know that there is an attack or there is a breach, to be able to patch it more securely. And the way to do that is through cloud, right? Because a cloud provider, whether it's Google, Oracle, Microsoft, Amazon, they can patch those readily and steadily, right? Instead of us reaching out to individual folks who have, servers and say, you should go patch this or you should go patch that, and waiting for that feedback from vendors and customers. I think the easiest way to do that is to put your stuff on the cloud so that as patches come along, they're automatically updated and installed, rather than waiting on folks to gather your data. So, recently there was a breach in servers, like in a 2003 email server. And had that been, the cloud wasn't breached, it was individual server racks that were breached. And so I think there's going to be a time when a lot of folks move to just public cloud or private cloud or hybrid cloud in that instantiation.
Yeah. Alex, one question to you about sensitive code protection. This is a topic that is at the heart of the CYSAT technology, especially in different deployments, public cloud, hybrid cloud, and so on. If you can explain a bit the concept of trusted execution environment, and maybe extend it to multi-party computation, or the concept of being able to process data in a secure environment.
Sure. So as I've spoke this morning, the concept of trusted execution environment is the fact of relying on some, let's say, on some part of hardware or software which you can trust, and running your code inside. So of course there are some challenges how you bootstrap things and etc. But yeah, that's basically the principle of trusted execution environment, and by extension of confidential computing. So on my side, I have one question for you, Akash, and then there is also one question from the chat. Actually, I was wondering. So of course, it's a very interesting attack model that you've presented on the AI. So actually, by the way, do you have any examples already where such kind of attacks happened on the on the data, to manipulate the model?
In real life, I cannot say that for certain. Usually, if the government has their data or models manipulated, they don't easily share that out with the public. So I don't quite know. I do know that it's very easy to do, right? I mean, our research shows that a simple, I think I had 163 million parameters, and of which I changed 3.
Wow.
And I changed those 3 by, 0.01% for latitude and longitude and wind only. And you can see how, if you changed it by 1% or 10%, like what that would look like in terms of, your hurricane might show that it's in Brazil instead of America. And so there's a lot of different ways to be able to throw these models off. For computer and vision, a lot of folks do what's called pixel and heat manipulation. So they add I think everyone's seen sort of the method where there's an AI model that tries to classify pandas, and then you change 1 pixel of that panda of a 4K picture, and it changes and then the AI model thinks that it's a gibbon or a monkey. The same thing with Tesla and stop signs, right? Humans automatically know when to stop because there's a stop sign, whether it's due to the shape or the color, where it's located on the street. You can put a simple piece of duct tape on any part of the stop sign, and the Tesla would stop recognizing that as a stop sign. And so there's a lot of different both software and hardware ways to attack AI models, and it's going to be crucial that we recognize as many of them as we can as we move into the phase of, everyone in every company, almost every product is using some type of artificial intelligence and machine learning. The more it proliferates, the more you're going to see these sorts of attacks on different attack vectors.
So by extension, actually, how you detect those? So I mean, in general, do you have some best practices or recommendations?
Yeah, so the best way we found out is what we call arbitrator in the loop. So usually it's a separate program algorithm or a human that's verifying sort of these cases. So I mean, for example, if a satellite is taking a picture of a tank and it classifies it as a human or a separate program might be programmed to say, let me check or verify the initial AI algorithm's answers. And so the more you have humans in the loop in this process, the better your results, but also the slower your results, right? And so there's kind of a dimensionality of how fast do you want your results and how fast do you need them versus how reliable and secure do you need them, right? If you can get 90% results within a second, or you have to wait, a day for 99% results, what are you going to take as a business leader? Those are implications that you have to take into account for your own business model.
Okay, so we still have hope for humans in the AI world.
Yeah, I'm hoping. Otherwise, I'll be out of a job soon.
Okay, so Matthew, do you have any?
There is one more question in the chat. I don't know if you saw it coming.
Do you want to handle it?
Yeah, and I had also one more for you, Akash. Maybe I'll go up with mine. I don't know how much you dug into that, but we're talking about AI, ML models actually running on spacecraft. Are we talking about similar threats, or is it completely different? Or
yeah, it's sort of similar threats in that, you have to, there's not a lot of AI being done on spacecraft. So I'm not sure how much you know about AI hardware, but a lot of it is run on what we call GPUs, graphical processing units. And so GPUs are very rare in space because they have to be what's called rad hardened or radiation hardened. And so in LEO, that's less of a problem, but when you start getting to the outer orbits, when you get out of the Earth's protection for solar activity, you start having to rad harden specific individual parts. And that research and development from a hardware perspective hasn't been done or is still being currently worked on. So there's not a lot of GPUs in space to be able to do the sort of AI model generation. Now, what you can do is put AI models on a CPU, but they run drastically slower. And so then it's can I get my data down quickly to Earth and then be able to process it on an Earth GPU faster than I can on a spacecraft CPU. And so, a lot of the things that we're talking about there's a need for hardware upgrades in space, specifically on the GPU front. And then does it matter if I can increase my bandwidth for uplink and downlink between my satellite or my space asset and the ground?
Yeah, and I guess that's also one of the benefits of the integration of the AWS and Azure orbital services to connect closer satellites and data analytics, AI, ML services that are being offered off the shelf.
Yep, exactly.
Alex, do you want to go ahead with the last question from the chat?
I think it's more like a comment.
Okay.
So it's about SnapR, SIPFish, PassGAN, and DeepLocker that are actually active AI threats. So I don't think if you have any comments on that, Akash.
I'm sorry, I didn't hear quite what you said.
So actually the comment, so it's not a question, but the comment, it's saying that SnapR, SIP, Fish, PassGAN, and Malgan, DeepLocker are active AI threats. So I don't know if you heard about this. At least, well, I'm not an AI expert, so that doesn't say much to me, at least.
PassGAN is the only one that I've heard about, and and GANs are sort of newer in this field, but we do use them to generate those types of neural networks. But a lot more research of it. That's not my specialty, so I couldn't comment one way or the other.
Okay. Do we have time to take this last one that just came up?
Sure.
This one is how about explainability of ML algorithms run on board? I don't know how much you can comment on that, Akash.
I missed before the ML algorithm.
How about explainability of machine learning algorithms run on board?
Yeah, so that was one of the other things, is that there's not a lot of machine learning algorithms being run on board in general. But I would say from an explainability perspective, there are a lot of third-party application software that are diving into the explainability of AI, right? And so even when you look at neural networks as a whole, like, when do you as a human being know that something is right? It's the collection of your past experiences. It's a collection of, what you've seen before, what you've heard before. But you can't go back theoretically and pinpoint, this experience is exactly why I'm thinking about this today in this way. So from an explainability perspective, right, neural networks in general were never created to go back and trace what's going on, because when you get to the hundreds of millions and billions of parameters, you're spending more time on sifting through that data than collecting side information on, this particular data instance was saved, this one was not. But there are companies like Darwin AI out of Canada is doing a lot of work in this field.
Yep. Okay, and also it connects a bit with the panel this afternoon, because we'll have Kees van der Poel from ClearSpace, and I know ClearSpace has been working with the PFL to develop an AI model that will be actually responsible for the proximity operations, because they're trying to actually dock or capture an orbital debris and take it down. And I know they will be running some quite sophisticated AI model on board the spacecraft. I don't know if there will be actually flying GPUs. We can ask Kees this afternoon.
Yeah, you should ask them.
Yeah.
Sure.
Anyway, yeah, exactly. Thank you so much, Akash. It was great to have you. Thanks for connecting. Thanks for being part of CYSAT 2021.
Yep. Thank you.
Thanks, Akash.
For having me.
Thank you.